Okay, so it looks like the lecture is being recorded and we're finally ready to start. Okay, so again, raise your hand if you have questions. So this is lecture 16. And so last time, we introduced eigenvectors and eigenvalues. So we said, what these things are. And in particular, we said that, a scalar lambda is an eigenvalue if there's a vector which has to not be 0. So that's called an eigenvector, such that this equation is satisfied, ax equals lambda. That's it's the eigenvector equation. What it says is that A doesn't change the direction of x. And after introducing this definition, we talked a lot about how to find these eigenvalues and eigenvectors. In particular, we described a two-step algorithm that does this. So the first step of the algorithm is find all the eigenvalues by solving a polynomial equation, the characteristic equation, which is determinant of A minus lambda I equals 0. So in the last lecture, I used the variable t instead of lambda. And the name of the variable doesn't matter, but there was some confusion on Piazza, so let's just use lambda to be consistent with the book. Okay, so this is the characteristic equation. And the polynomial that appears here is the characteristic polynomial, and the eigenvalues are the roots of this equation. The roots of the characteristic polynomial. And then once you have the eigenvalues, this problem just reduces to row reduction. Like once you know what these special values lambda are, then you just find the eigenvectors. And specifically, the reason it boils down to row reduction is that the set of eigenvectors corresponding to any eigenvalue, which is called an eigenspace, is just a null space of this matrix A minus lambda I, where lambda is an eigenvalue. So that's how you find eigenvalues and eigenvectors and what they are. And then finally, we discussed how many are there, how many solutions are there. And we derived some basic bounds on how many solutions there can be. So there are at most n eigenvalues, and that is counting multiplicity. And multiplicity means the number of times that eigenvalue appears as a root of this characteristic polynomial. And the reason for this is just a fact from algebra. If you have a degree n polynomial, then it has at most n roots. Another easy fact, actually much easier fact, is that there are at most n linearly independent eigenvectors. And okay, I should specify what n is. So all of this stuff is an eigenvalue of an n by n matrix A. So it only applies to square matrices. And then certainly these eigenvectors will live in Rn, and so you can't have more than n linearly independent vectors in Rn anyway, so that gives you an upper bound. And then we derived one nice sufficient condition for when actually both these bounds are met. We showed that if there are n distinct eigenvalues, then the corresponding eigenvectors are linearly independent. Okay, so it looks like there's one question. So let me Yes.
Hi.
Hi.
So why is only n by n matrices applied to this?
Okay, that's a good question. So the question is, why does this only apply to n by n matrices? Well, the reason is, just look at this equation, right? So in order for this equation to make sense, the vector on the left-hand side has to have the same dimension as the vector on the right-hand side, right?
Oh.
So if A was m by n, then ax would live in Rm, right?
Right.
But it has to equal a multiple of x, so m has to equal n.
Okay, gotcha. Thank you.
Yep. Okay. So this is what we discussed last time, and we also discussed wait, let me move this up a little bit. We also had one more fact, which is, well, even if there aren't distinct eigenvalues, you can say something about the number of eigenvectors and how it relates to the algebraic multiplicity, which was that if lambda is an eigenvalue, then the dimension of the eigenspace, which is something which measures the number of linearly independent eigenvectors of the eigenvalue, this is at most the algebraic multiplicity of lambda. These are some facts about how many solutions we expect to have to this eigenvector equation. So in this lecture, what we're going to discuss is two questions. So one is operation of preserve eigenvalues. Okay, so remember at the beginning of the course, we did row operation. We did linear systems, and we observed that row operations preserve the solutions of AX equals B. Now, we saw at the end of the last lecture that not row operations, right? Row operations can really screw up the eigenvalues. So we'll understand which operations preserve the eigenvalues. And then the second thing we understand is, why are we doing it? Right? So we defined this equation and we talked about how to find solutions. What's the point? And this is something that's called diagonalization. And it's, in some sense, one of the main applications of linear algebra, one of the most important. Yes. You have a question?
Yeah, I don't know if this is happening for everyone, but it seems like when you lean forward to write, the mic starts to cut out.
Oh, really? Okay. Let me. You mean when I start writing or when I lean forward to write?
Yeah, like when you're leaning forward to write. I don't know if that's happening for everyone else though.
Is it happening for other people? Okay. Okay. I'll just try to stay close to the mic. Let me know if it happens again. Okay. So let's now address these questions. So the first question, which operations preserve eigenvalues, is something that goes by the name of similarity. And this is a new kind of transformation of matrices that's different from row operation. And here's the suppose I have two n by n matrices. So an n by n matrix A is similar to an n by n matrix C if P inverse A P equals C for some invertible matrix P. Okay, it better be invertible because I wrote P inverse here, right? And I should observe that this is actually equivalent. I mean, there are two ways of writing this. So one is I can multiply A on the left by P inverse and on the right by P and say that that should be equal to C. But this is equivalent. So if I multiply this equation on the left by P and on the right by P inverse, then I get some cancellations, and this is equivalent to the equation A equals P, C, P inverse. This is just matrix algebra. So these are two equivalent equations, and that's what it means for two matrices to be similar. So, one simple observation is that if A is similar to C, then also C is similar to A. So why is that? Anybody know? Yeah. So why is that?
Oh, why is that? It's because in this case, look, the P inverse that goes at the beginning is now P.
That's right, exactly.
The
So,
rules are reversed.
so the point is that the second equation actually satisfies the definition of similarity, but using P inverse instead of P, right? Because the second equation is that P inverse times C times P inverse for A. The similarity is a symmetric notion. If one matrix is similar to another, then the vice versa is also. So that's what similarity is. And what does similarity mean? Well, P inverse AP is equal to P. Well, P is invertible, right? So let's just write out the columns of P and give them some names. So the columns of P are, let's call them B1 to Bn. And now these columns are going to be linearly independent, right? Because P is invertible. So actually they're going to be a basis because they're n linearly independent vectors in Rn. An invertible matrix is the same, is in direct correspondence with a basis just by looking at the columns. Yes. You have a question?
I do not have a question.
Oh, sorry. Oh, I guess I have to lower your hand. Okay, good. So, okay. Okay, good. So now let's interpret this equation we've written here as an equation about change of coordinates. What is A? Well, I can interpret A as the standard matrix of a linear transformation, which is just multiplication by A, right? So I'm using this notation to mean the linear transformation that's multiplication by A. I mean, that's what the interpretation of the matrix is, right? It's a standard matrix of some linear transformation. Now, what about this matrix P? Well, if I put a bunch of basis vectors in the columns of a matrix, then what does that really mean? Well, when I multiply that matrix by a vector, I'm just taking a linear combination of those columns, right? So what I'm really doing is I'm changing coordinates from a B coordinate vector to an E standard basis, because I can interpret these B1 through Bn are just vectors written in standard coordinates, but they're the basis vectors of the B basis. Similarly, P inverse, what is that? Well, that's the linear system you solve to turn something from standard coordinates to coordinates in the B basis. So this is actually the change of coordinates matrix P of E goes to B. This is all coming just from the change of coordinates lecture. So what's the conclusion? Well, if you use this interpretation and rewrite that equation, you actually get that P of E goes to B applied to A in the E basis times P of B goes to E is equal to C. It's literally the same equation. But what does this mean? Well, this means that actually C is just the matrix of A in the B basis. So this funny thing where you multiply by inverse on one side and by the matrix on the other side, this corresponds to writing the same linear transformation on a different basis. So the meaning is that C is the matrix of A, that means multiplication by A, in the B basis, by which I mean input and output basis. Okay, so the meaning of similarity is just you're writing the same linear transformation in a different basis. And if you wanted to draw a little picture, as we've been drawing, it would be something like this, that A is a linear transformation from Rn to Rn. But now if I change into this B basis, so I write everything as B coordinate vectors, and this matrix is P inverse, this matrix is P, and this matrix is C. So I'm just saying that if I look at what, this equation up here corresponds to this picture down here, that C is the matrix of A in the B basis. So this is P of E goes to. Okay, any questions? Yes. Yes, do you have a question?
Yeah, so when you write like A in terms of E on both sides, does that just mean that you're taking a vector in the standard basis, applying E to it, and then you get an output of something in the standard basis also?
Exactly, yeah. So,
Okay.
so the point is that, when we write AX, right, what do we mean? We really mean AX in basis. When we write X, what do we mean? We really mean the standard basis.
Okay, yeah.
So the matrix that takes AX to AX is A. And that's what I mean by this notation. Does that make sense?
Yes.
Any other question? Okay. So that's the meaning of similarity. And now I want to say what it has to do with eigenvectors. If A is similar to C, then they both have the same eigenvalues. With the same geometric multiplicities and algebraic multiplicities. The geometric multiplicity, remember, means a dimension of the eigenspaces corresponding to these eigenvalues. Algebraic multiplicity means the number of times it appears as a factor in the characteristic polynomial. Okay, so similarity preserves all of these properties. Yes, do you have a question? Hello? So let's see a proof of this. Well, there are two parts. One is geometric multiplicities and second is algebraic multiplicities. So let's see the proof of geometric multiplicities. Well, so again, the assumption is, let me erase this. So assume P inverse AP equals C. In other words, C is just the matrix of A in this B basis, where P, is a matrix whose columns are this B basis. So how do we prove the first fact? Well, when is something an eigenvector of A? Well, it's when AX equals lambda X, and X is not 0, right? That's when something is an eigenvector of A. Well, that's an equality of two vectors, right? So by the correspondence principle, this is true if and only if it's true after I change to B coordinates, after I change to the B basis. So this is true if and only if the matrix of A in the B basis times the coordinate vector of X in the B basis is equal to the coordinate vector of lambda X in the B basis. But wait a minute, lambda is just a scalar. So this is just lambda times the coordinate vector of X, the B basis. And wait a minute, we just checked, right, that C is equal to the matrix of A in the B basis. So this equation is actually the same thing as saying C times the coordinate vector of X in the B basis is equal to lambda times the coordinate vector of X in the B basis. And again, this vector is not 0. But that's what we wanted, right? This is exactly what you need for lambda to be an eigenvalue of A. And this is exactly what you need for lambda to be an eigenvalue of C. So whenever lambda is an eigenvalue of A, it's an eigenvalue of C, and vice versa, just by the correspondence principle. Similarity is just change of basis, and that doesn't change the validity of the eigenvector equation. I'm not saying that they have literally the same eigenvectors. They actually have different eigenvectors, right? The eigenvector of A is X. The eigenvector of C is the coordinates of X in the B basis, which is not exactly the same thing. I mean, it's not the same thing. And again, applying this to the entire null space, you get that the dimension of the null space of A minus lambda I is equal to the dimension of the null space of the matrix of A in the B basis minus lambda I. By the way, I should say that there's one matrix that doesn't change in any basis. It doesn't matter. You can change the basis, and the matrix of that linear transformation with respect to any basis is the same. What linear transformation is that? Well, I kind of implicitly said it here, right? I didn't put brackets around identity. Any thoughts? Well, okay, I'm implicitly using that the matrix of the identity in the B basis is just the identity. And you can check this using the change of coordinates formula. Yes? Hello? Do you have a question? Okay. Okay, so that's the proof that they have the same geometric multiplicity, which is the dimension of these eigenspaces. Next, I'll do the proof that they have the same algebraic multiplicities. I'm actually going to show that they have the same characteristic polynomial. Which will imply, in particular, that all the roots are the same. This is actually a different proof that the eigenvalues are the same, but they're now the algebraic multiplicities. So what's the proof? Well, left-hand side is this, determinant of A minus lambda I. But what do I know? I know that they're similar. So I know that A equals PCP inverse. So I can substitute this, and I get that this is, by the way, the characteristic polynomial. Okay. This is determinant of PCP inverse minus lambda times identity. Now I'm going to do something a little funny. I'm going to write that as lambda times P identity P inverse. I can do that, right? Because P times P inverse is identity. They cancel. Right? Okay. So what's the next step? Any thoughts? So I want to turn this into the characteristic polynomial of C. How would I do that? Yep.
Well, I would use the multiplicative property of the determinants of.
Great idea. Great idea. So what you're suggesting is you need to do a little bit of matrix algebra to factor the P and P inverse out. So this becomes P. So I take the P out of the left-hand side and P inverse out of the right-hand side. And you see that this is P times C minus lambda I times P inverse. You just pull the P and P inverse. Okay. And now, again, determinant is multiplicative. So this is determinant of P times determinant of C minus lambda I times determinant of P inverse. But determinant of P inverse is 1 over determinant of P. So these cancel. And indeed you get this. Okay, so it follows immediately from the multiplicative property of the determinant. So here, the thing I use here is that, det xy. So similar matrices have the same characteristic polynomial. Okay, so that completes the proof of this theorem. And it gives us an understanding of what kind of operations you can do on a matrix while preserving the eigenvalues of the matrix. So now I'm going to focus on, well, I guess I'll move to the last part. And remember that our original motivation that I presented for studying eigenvalues and eigenvectors. Oh, sorry. Do you have a question?
Hello. Yeah,
hello?
hi.
Yeah.
I had a question about like similarity in general. Like it seems like it seems fairly like an arbitrary relationship. Like did the definition of similarity come from the eigenvalue properties?
Good question. Good question. So the question is, it seems like a weird definition. What's the conceptual way to think about it? Well, for me, the meaning of similarity is captured by this. Two matrices are similar if they describe the same linear transformation in different coordinate systems. So that's sort of a, that's a thing that that's an inherently conceptually meaningful thing, right? If you have a linear transformation, we discovered that you can describe it in all these different bases, right? It has different matrices with respect to different bases. And similarity just means that these two matrices are describing the same linear transformation in different bases. Does that make sense?
Yeah, thank you.
Yep. Any other? Okay. So yeah, maybe I should put this in star. This is really the meaning of similarity. And yeah, a consequence of that meaning is that if two matrices are similar, they have the same eigenvalues, also with geometric and algebraic multiplicity. Okay, so now we get to diagonalization, which is why are we doing all of this? Well, the reason is, so remember a few lectures ago, we asked, you can write in many different bases, what is the best basis in which to write the matrix of a linear transformation. And sorry, this is like some notes. Okay. And the answer turns out to be the basis of eigenvectors. if there is such. So let me write a definition. So a matrix A n by n is diagonalizable if it is similar to a diagonal matrix. And algebraically, that means that, you know, P inverse A, P equals D for some P invertible and diagonal D. And conceptually, it means that there is some basis P of Rn such that the matrix of A in that basis is diagonal. And we saw in the previous slide that these are the same thing, right? Being similar to a diagonal matrix means that there's some basis in which the matrix is diagonal. Now, why do we like diagonal matrices so much, right? Well, let's just look at what a diagonal matrix does to a vector. So this is a diagonal matrix. If you multiply it by a vector, x1, x2 with x3, well, it just does something very simple. It multiplies each entry by a number separately. So you get x1, 2x2, and 3x3. And the way to articulate that is that it acts on the coordinates separately. And by separately, I mean that there is no interaction between the coordinates. So if you look at what this matrix does to these coordinates, it never mixes up x1 and x2 or x1 and x3. It just does something separate to each coordinate, which is very simple, just multiplication by a number. Now, these matrices are really easy to understand because essentially you just need to understand how to multiply numbers. You don't actually need to understand linear algebra to figure out what a diagonal matrix does. And so being diagonalizable is great because you can turn a complicated matrix into a really simple one, namely a diagonal one, without changing the meaning, right? Because similarity is just changing the basis. You're still doing the same linear transformation. You're just changing your frame of reference. So maybe this will become clearer with an example. So it's literally the example from the last lecture where we computed the eigenvalues and eigenvectors. So let me write down what this example is. Yeah, so the matrix was this, right? 1, 3, 3, minus 3, minus 5, minus 3, 3, 3, 1. It had a characteristic polynomial, I believe minus lambda minus 1, lambda plus 2 squared. So in particular, the eigenvalues were 1 and minus 2. And the eigenspaces, which we calculated, were E1 was the span of this vector, 1, minus 1, 1. And E2 was the span of, so it's called vector V1, was the span of the vectors minus 1, 1, 0, and minus 1, 0, 1. Let's call these V2 and V3. So the first eigenspace has algebraic and geometric multiplicity 1. So let me rewrite that over here. Okay. And the second one, well, it has geometric multiplicity 2 because there's a basis of 2 vectors for this eigenspace. It also has algebraic multiplicity 2 because this factor appears as a square. So here the algebraic is equal to geometric multiplicity is equal to 2 for the second eigenvector. So now, by a theorem in the last lecture, we know that if the sums of the geometric multiplicities is n, in this case 3, these must be linearly independent. So by the theorem in the previous lecture, we conclude that V1, V2, V3 is a basis of R3. So we actually have a basis of eigenvectors. This is sometimes called an eigenbasis. Now, let's see what happens if we write. So this is a complicated matrix, right? A. If you look at what AX is, so if you multiply A by some vector x1, x2, x3, it doesn't have this nice property of the previous one had, right? You get x1 plus 3x2 plus 3x3 minus 3x1 minus 5x2 minus 3x3, etc. So in particular, what A actually does to the vector is not so clear, right? Because in particular, the coordinates interact. But now let's write the matrix of this in the B basis, where I choose B to be the eigenvector. What is the matrix of A in the B basis? Well, we figured out how to do this a couple of lectures ago, right? Change of base, change of coordinates for linear transformations. Well, that's just going to be A applied to each of the basis vectors, but now written in the output basis, which is also B. Let's figure out what that is. Well, this is where you use that they're eigenvectors, right? Because they're eigenvectors, multiplying by A just multiplies these vectors by a scalar. So you actually just get 1 times V1 minus 2 times V2 and minus 2 times V3. And what is that? Well, remember, you have to write everything in B coordinates. So what are the B coordinates of V1? Well, they're just 1, 0, 0. What are the B coordinates of V2? They're 0, 1, 0, but now multiplied by minus 2. So you get a minus 0, minus 2, 0. And what are the B coordinates of V3? Well, you get 0, 0, minus 3, which is diagonal. Okay, so this is the punchline. And you can reduce. So let's call this matrix D, right? So I just proved that A is similar to a diagonal matrix, and the similarity was given by the eigenvector basis. And the whole point of this diagonal matrix is that this is now, it's this acts separately on the different coordinates, right? So coordinates are decoupled. So, I'm sorry, there's a question. Do you have a question? Hello? Somebody raise their hand. Joanna, do you have a question? Or? No, okay.
Hello.
Sorry, do you have a question? Hello?
Can you hear me?
Yeah,
Hello?
I can hear you.
You found the the coefficients before v1, v2, v3 for the matrix using the values you found for your eigenvalues, right?
Exactly.
Okay.
So I'm replacing, I mean, after all, what is the eigenvector equation? It's the equation that A v1 equals the eigenvalue, which is 1 in this case, times v1, right?
Yeah.
A v2 equals minus 2 v2. And this is the whole game, that you go from a matrix to a number.
Yeah. Okay, got it. Thank you.
Okay. So, so the point is that this is not an accident, and this always happens. Is diagonalizable, which means similar to a diagonal matrix, if and only if A has n linearly independent eigenvectors. And in this case, it's very explicit. The correspondence is very explicit. So come in the proof. Well, let's assume it's diagonalizable. Let's actually start from the bottom. So A V, let's suppose A V1, let's suppose A has n eigenvectors. So that means A V1 equals lambda 1 V1 all the way up to A Vn equals lambda Vn. They may not be distinct, but I'm not requiring them to be distinct, right? In the previous example, the eigenvalues were actually not distinct. But I'm requiring these vectors to be linearly independent. So suppose you're in this situation. That's the bottom case, right? Of having n linearly independent eigenvectors. Well, let's put these eigenvectors in a matrix. So let's form a matrix P with just these eigenvectors as columns. And now let's form a diagonal matrix D with the eigenvalues as the entries. Right? Then, what I can do is I can write all of these equations in a matrix notation. Right? So I have that A times the matrix P is equal to the same thing, but now all the columns are scaled, right? That's what it means to be eigenvectors. I'm just rewriting the same thing in matrix form. But now here's a little algebraic insight that you have to have. This is literally the matrix P times the diagonal matrix T. You can just check this for yourself. Just do the matrix multiplication, right? Like this lambda 1 always multiplies an entry in the first column. That's the idea. But now this equation, I mean, what is this equation? Well, this equation is that AP equals PT. And P is invertible, right? Because they're linearly independent. But now by multiplying by P inverse, you get that P inverse AP equals. And that finishes the proof. So it's almost literally the same statement. You just put the eigenvectors in this matrix and the eigenvalues in this diagonal matrix. And then just writing it in matrix form gives you the similarity equation. So that's not an accident. The eigenvector basis is always the basis that gives you a diagonal matrix. And this is why the eigenvalues are so important. They really reveal, you know, what the matrix, what the linear transformation is in its simplest form. Yes. Do you have a question?
Yeah. Could you go back to the previous slide for a second?
Sure.
How do you get from the one where it's 1v1, negative 2v2, negative 2v3 to the last one with all the zeros?
Good question. So the question is, how do you do this this last step? Right? So let's do it over here. So what does coordinate vector of v1 in the B basis mean? Well, it means express this vector as a unique linear combination of the basis vector, right? So let's express v1 as a unique linear combination of the basis vector. 1 times v1 plus 0 times v2 plus 0 times v3, right? So what that means is that the coordinate vector of v1 in the B basis is 1, 0, 0. And that's why I have 1 times 1, 0, 0 here. Does that make sense?
Yeah, that makes sense.
So for v2, it would be in the second entry because it's a second vector. Does that?
Yeah, I understand.
Okay.
Thank you.
Okay. Any other? Okay, there are a bunch of questions. Let me, how does this work? Hello? Yeah, do you have a question?
Yeah, I was wondering if this is still possible if one of the eigenvalues is equal to 0.
Good question. Absolutely. This is possible if one of the eigenvalues is equal to 0. So let me make a separate slide. For example, matrix, its eigenvalues are 1 and 0. It's already diagonal. Its eigenvectors are just the standard basis.
Okay.
So 0 is not special from an eigenvalue point of view. It's special from an invertibility point of view. But, you know, it's another scalar. Does that make sense?
Yeah. Thank you.
Yep. Hi.
So just going off of that, wouldn't that mean that the eigenvectors aren't linearly dependent though?
Your question is, if there's a 0 eigenvalue, wouldn't that make the eigenvectors linearly dependent?
Yeah.
Well, let's think about this example, right? The eigenvalues are 1 and 0. And the eigenvectors, v1 is just this, and v2 is just this.
Oh, okay.
There's no, yeah, the eigenvectors, yeah. So, okay, so maybe I'll make this important remark. Matrix A is diagonalizable if and only if you have n linearly independent eigenvectors. A matrix A is invertible if and only if lambda equals 0 is not an eigenvalue. What do these two have to do with each other? They have nothing to do with each other. This is a statement about eigenvectors. This is a statement about eigenvalue. Which means you can have one but not the other in every combination and so on. Okay? It's a little confusing because, of course, 0 can never be an eigenvector, right? That's in the definition.
Yeah.
But the 0 eigenvalue does not really have a special meaning from a diagonalizability point of view. It has a special meaning from an invertibility point of view. Yep. Is that okay?
Yeah, thank you.
Okay, great. Any other? Hello?
Yeah, so, excuse me. When we were talking earlier about the best basis, we mentioned that it's the basis of eigenvectors if they exist, but what if no such basis exists?
That's a good question. Not every matrix is diagonalizable, right? So what if eigenbasis does not exist? Well, then life is hard. I mean, you know, this is I mean, you can't do this, is the conclusion. In the next lecture, we'll see a way to expand the set of matrices for which you can do this by using complex numbers. But there really are matrices where you cannot do this, and they are not diagonalizable. And they're really hard to deal with. Like, I should say, okay, they don't come up much in large swaths of math. For example, I never actually worked with a non-diagonalizable matrix till like 3 years ago. But now, I mean, in some areas, they're really important. And then, yeah, this just doesn't work. You have to do something else.
Thank you.
Yep. Okay. Any other? Hello?
Hi. Someone asked a question earlier in the chat that never got answered. They said, are similar matrices row equivalent?
No, they are not. So so let's write it. So the question: similar matrices row equivalent. And the answer is, well, no, definitely not. But can you think of an example or not? So remember, similar means A equals PCP inverse. So, okay, I mean, okay, so I encourage you to find an example of this. It's not very hard. You can even find an example where, find an example where X is in the null space of A, but not in the null space of C, for example. You can try to do that. But at a higher level, I mean, remember, row operations, like the basic idea in row operations is that this remains true if you multiply by an invertible matrix on the left. This is the idea of row operations. We didn't emphasize this, but row operations can always be thought of as multiplying on the left by an invertible matrix. Similarity, you multiply both on the left and right. So, I mean, the short answer is no. I mean, I can write an example, but verifying that it is an example is just going to require more algebra than I want to do right now. So you can try to come up with one by yourself. Is that okay? Hello? Hello?
Hi.
I
had a question on the slide that had the eigenbasis on it, the V1, V2, V3, 2 slides ago.
Yep. This one?
Yeah, that one.
Yeah.
I was curious as to how you got E1 as a span of
I'm sorry.
vectors, E2 is a span of 2 vectors, and then combine them. I'm not understanding where those two
okay.
spans
So
came from.
I also made a mistake. This is -2 because the eigenvalue is -2. But yeah, but your question is why you're somehow confused by the fact that these two came from one eigenspace, right? E-2, sorry.
Yeah.
Yeah. So the point is, for this construction to work, all I need is that the eigenvector equation is satisfied on this basis. I don't really care that they came from the same eigenspace.
Okay.
Like this part is just, it's just a general formula essentially for finding the matrix of a linear transformation with respect to a pair of bases, right? Yeah. So what I did is I chose B to be the input and output bases.
Okay.
I mean, okay, since this is very important, let me give you an alternate proof. Think about what A does to a vector X, right? Well, you can write X as a linear combination of V1, V2, and V3 because it's a basis, right?
That makes sense.
So so now by linearity, this is just C1 V1 plus C2 V2 C3. And it doesn't matter where these came from. It just matters that they're a basis. So now by linearity, you get that this is C1 A V1 plus C2 A V2 plus C3 A V3. But now you use the eigenvector equation to turn these into scalars. So it's a C1 times 1 times V1 plus C2 times minus 2 times 2 plus C3 times. And so now if you see what A did to the coordinate vector of X, right? The coordinate vector of X in the B basis, in this case, was C1, C2, C3. But what was the coordinate vector of AX in the B basis? Well, it's the vector C1 minus 2C2 minus 2C3. So combining these two facts, you get that the matrix has to be what I wrote. Does that help?
Yeah, that helps. Thank you.
Okay, great. Any other question? Hello?
Hello. Do
Oh,
you mind
hi.
going to the last slide the person had a question on?
Sure.
Oh, the last slide.
Oh, this one? Or
Oh no,
this one?
the next one. Okay, this one. So my question
This one, yeah.
is, oh wait, not this one, the last one.
Yeah,
Okay, so oh wait, sorry.
Sorry, the next one?
Yeah, the one that you were at before.
This one.
Yeah, okay, for this one. So my question is, if you have two, so it seems that V1 plus V2 equals V3. So are they still linearly independent?
Oh, wait a minute. Is there a typo? No, V1 plus V2 does not equal V3, actually. Right? I mean, there's a -1 up here.
Oh, okay. And then my next question would be, if you have a scalar or algebra or geometric multiplicity, will they always give you a linearly independent eigenvector?
So in the previous lecture, they're only linearly independent if all the geometric multiplicities are equal to the algebraic multiplicities.
Okay.
If any of the geometric multiplicities is lower, as in some examples in the previous lecture, you won't have enough eigenvectors.
Okay.
And this speaks to the question somebody else asked, that what if you don't have a basis of eigenvectors? Well, then you can't do this.
Okay.
Is that okay?
Yes, thank you.
Okay. Yep. Okay, so it looks like, okay. Okay, so that is the main theorem about diagonalizability. And conceptually, what this achieves is something that I like to call. This terminology is not used in the book. It's not like something we're going to use mathematically, but it tells you why this is so cool. And what's going on is, if you have a matrix that's a linear, that gives by multiplication by the matrix a linear transformation from R to Rn. Well, in general, that matrix might have all kinds of entries, right? You might have you can think of it as coupled, which means that the coordinates interact. And if this is an n-by-n matrix, this is some sort of n-dimensional, I don't know, process, let's say. And what diagonalization buys you is by switching to the eigenbases, it gets you a matrix that looks like this. It's diagonal, and the conceptual difference is that this is decoupled. It's really not an n-dimensional process. It's a bunch of one-dimensional processes, right? N one-dimensional processes, which are much easier to understand. So this is why diagonalization is, I mean, it's really like a very deep thing. You can argue it's the most important theorem in all of math, for example. I mean, as you go on, you'll probably see why. Anyway, let's look at a concrete example where this really helps us out. So here's so suppose every year there's some number of like skiers and snowboarders at Lake Tahoe, let's say. And given the snowboarders at Lake Tahoe. And let's say that initially, let's say there are 10 skiers. Okay. And there are 30 snowboarders. So these are the initial conditions. And now every year, let's say these numbers change due to some mechanism, right? So every year, the populations change as follows. Well, the number of skiers in year n+1 is the average of the number of snowboarders and the average of the number of skiers and the number of snowboarders in the previous year. Because, you know, I don't know. I mean, okay, half the skiers turn into snowboarders. You can think about why that might happen. But the number of snowboarders also changes. And every year the population doubles. But then, you know, some of them disappear, and the number who disappear is exactly equal to the number of skiers. Maybe they get hit by skiers or something. So this is what's called a discrete dynamical system. And it's a process in time, right? You have some initial conditions, and then you have some interaction between these two numbers. There's number of skiers and snowboarders, which, you know, is not super clear, right? What happens? And this is used to model various population growth. So it's used in biology, also used in epidemiology. It's probably used to understand coronavirus, something like that. But let's just imagine this very simple setup. Now the question you can ask is, what happens after 10 years? So in particular, what's the ratio of snowboarders to skiers? So initially there are actually more boarders than skiers. And with time, the skiers, you know, half of them are becoming boarders, the number of boarders is increasing, but it's also decreasing here because of this minus SN term. So what's going to happen in 10 years? Well, one idea is to set this up. So let x naught, x is not a vector which contains number of borders and the number of squares and xn be this B n at time n. And now the point is that the update rule that you saw on the previous slide, the relationship between the numbers at n and n plus 1 can actually be written as matrix multiplication. So let's write that as a matrix. So the rule says that x of n plus 1 is equal to some matrix, which can have half, half, 2 minus 1. So times xn. Let's call this matrix A. And now, therefore, what we're interested in, we want to know what happens at time 10, which is just a to the 10 times x naught. And you could do that, right? You could multiply this matrix 10 times, but this seems to require a lot of arithmetic. And again, the reason it's hard is that this is not a diagonal matrix, right? If it was diagonal, it would be easy. Hello? Hello?
Hi.
Do you have a question?
Yeah. So the rule for the matrix for the vector of x n plus 1, like how did that come about? Is that just like?
Oh, well, yeah. So let's think about. Let's just write these equations in matrix notation.
Oh, from the
right?
okay.
So this is saying that
right.
Sn plus 1, Bn plus 1 is equal to that matrix A times Sn Bn, right?
Right.
Oh, whoops. I'm sorry, I got it backwards. So so let's see, how do I want to do this? Okay. The problem is I put Bn on top. So actually this is going to be reversed. I'm sorry. Thanks for catching that. Okay. I mean, I just swapped the, right here I wrote S on top, and here I wrote B on top. So I should have just written these in the other order. Okay. But then does it make sense?
Yeah.
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 Okay. So the relation is you have your B of n, S of n, B plus 1, and S of n. And if you literally flip these equations, you get the matrix that's written here, 2 minus 1, half, half. Okay. So now the problem is reduced to just computing a high power of some matrix, which seems kind of annoying. So the idea is, well, let's diagonalize it. We know how to take powers of diagonal matrices, let's diagonalize it. Remember, we don't know if we can diagonalize it, so let's find the eigenvectors and eigenvalues. So step 1, we compute the characteristic polynomial. That's the determinant of the matrix 2 minus lambda, half minus lambda, minus 1 half, which is 2 minus lambda times half lambda plus a half, which is lambda squared minus 5 halves lambda plus 3 halves, which if you apply the quadratic formula is just lambda minus 3 halves and lambda minus times lambda minus 1. So from this you conclude that the eigenvalues are 3 halves and 1, and they're distinct. So by the previous theorem, you'll have linearly independent eigenvectors. But let's calculate them. Okay, so the eigenvectors, you have to do a little bit of row reduction. let's do it. So the 3 halves eigenspace is null space of the matrix minus half, 1, 1, which turns out to be the vector 2, 1. So let's call this V1. And the eigenspace for the other eigenvalue, which is 1, turns out to be the null space of the matrix minus 1, minus half, half, which is the span of, sorry, these should all be span of 1, 1. Let's call this vector V2. So now we're in business to apply the decoupling principle we thought about in the last lecture. If we now rewrite the problem in this basis, the eigenbasis, it should be diagonal. And okay, so we know that P inverse P we know that A equals A inverse for D containing the eigenvalues, which were 3 halves and 1, and P containing the corresponding eigenvectors, which are V1 and V2, so 2, 1, and 1, 1. That's what the theorem told us, right? You can diagonalize if you have enough eigenvectors. Sorry, is there a question? Hello? Hello?
Yeah, I was wondering how you got the null of those values.
Oh, well, you do row reduction, which I skipped. Oh, you mean why I got these matrices?
Yeah, why is it the null of those?
Oh, okay, yeah. Well, because remember, the matrix you put in is A minus the eigenvalue times I. So A minus 3 halves I, right? So if you calculate A, so A was this matrix over here. If you literally subtract 3 halves I from this, what do you get? You get this.
I see.
Wait. You should get that.
I think there was like an arithmetic mistake.
Yeah, there's an arithmetic mistake actually. You're right. There is an arithmetic mistake. Okay. Well, I pre-did these calculations. So let's check. So, well, okay. If you literally subtract 3 halves from here, you get half and minus half, right? So you actually get.
Is it minus 1?
Yeah, you get half and minus 1. Oh, okay. That's okay. You're right. That's correct. But that has the same null space.
Okay, thank you.
Thanks for catching that. Okay, so yes, this matrix better be A minus 1I. So let's check that. Oh my God, I've got some really weird. I mean, I think the null spaces are right, but the signs are all weird. So you should get 1 and minus half here, right? You should get 1 and minus half, which, okay, again, okay. I don't know how I got those matrices, I'm sorry. But okay, thanks. But is it clear now?
Yes, it's clear, thank you.
Okay. Those were arithmetic mistakes, but apparently I did something right because you get the same eigenvectors. Anyway, so once you have these, now how am I going to compute a to the 10 times x naught? Well, the point is that that's PDP inverse times PDP inverse times PDP inverse 10 times x naught. But now watch this. All these P inverses in the inside cancel. They're just identity. So it's literally just P times D to the 10 P inverse. This is the whole game, right? That you reduced powering A to powering a diagonal matrix. And now I can calculate this. So what's P inverse x naught? Well, I need to write x naught, which is x naught was my vector 30, 10. as a linear combination of v1 and v2, it's actually just turns out to be 10 times v1 plus v2. Is that right? No, that's not right. Okay. So, okay, I want to write this as a linear combination of v1 and v2. Well, I technically need to row reduce. Does anybody see how to do it? Okay, well, okay, fine, let's do it. Maybe I should use a calculator. Okay, fine. I'm running out of time, but I'm just gonna row reduce it here. So you have 2, 1, 1. Let's just do 3, 1 because it's the same as 3, 10. So now you subtract half the first row, so you get minus half, right? So then what do you get? You get that x2 equals minus 1. You get 2x1 plus x2 equals 3, which means x1 equals 4, 2 equals 2. Okay, so this is actually going to be twice the first vector, 20 times, minus 10 times the second vector. Okay. Okay, let me erase the row reduction for now. Okay. Okay, so that checks out. Okay, and now I'm happy, right? Because that means that P inverse of x naught is this vector 20 minus 10, right? So that means that this is equal to P d to the 10 times the vector 20 minus 10, and which I can easily compute. So this is P times the vector 3/2 to the 20 times 20, and the other one is 1 to the 10 times minus 10. Okay, and then if you take the linear combination, that's like 3/2 to the 20 times 20 times the vector 2, 1 minus 10 times the vector 1, 1. And this gives you a pretty good answer, right? Like this is exponentially large. This is small. So the conclusion is that the ratio of the number of borders, the number of spheres, is about 2 to 1 after 10 steps. This is the benefit of diagonalization. This is what I mean by decoupling. You turn it into a process where you have two things that don't interact, namely these two blocks. So anyway, I'll do more next time, but that's it. And by the way, no office hours today, they're postponed till tomorrow. Sorry about that.
God.
Oh, are there more questions?